Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we are very pleased to have Adam Kalai here. He is here from TTI, and he is going to talk about towards agnostically learning half spaces.
Okay, thanks a lot. Okay, thank you. So actually, this is not the talk that I'm giving, and this is not my general audience job talk. Here I decided just to give a regular talk about a paper that I did to mix things up. So this is a talk on a learning problem, and this is joint work with Adam Clivens at the University of Texas at Austin, Yishai Mansour in Tel Aviv, and Rocco Cervedio at Columbia. Okay, and I'm going to talk about a basic problem in learning called the problem of agnostically learning half spaces. And this relates to these Fourier learning algorithms that some people may have heard of, but I'm going to describe them anyway. So hopefully you'll find something interesting. Okay, so let me start by defining a model of learning called the PAC model of learning, defined by Valiant. Okay, so this is a very simple model of learning of a family of functions. So you have some set x in a family of functions, Boolean functions. Okay, and you have some distribution over x. Okay, which we'll denote by mu. And okay, and so okay, sorry. Okay, and then you have some function in the family, and what basically is happening is you're getting examples drawn from this distribution. So x is drawn from the distribution, and you're getting a label y, which is the value of the function at this point. So you should think of this as, let's say, you've got patient records, and you're trying to predict whether they're going to get diabetes or not. And you have their blood pressure and their cholesterol and their age and so on. And let's say that whether they get diabetes or not is a function, some function in this family of their attributes. So yi is either 0 or 1, and it depends on their attributes, and it's deterministically this way. And so the goal here is you get a bunch of labeled data, training set drawn from this distribution and labeled according to the function. And you output another function, h, which is going to make predictions on future patients whether they're going to get diabetes or not. Okay? And of course, you would like the future predictions to be accurate. And so you would like, in fact, to have error less than epsilon, ideally, where error would be defined in this sense. So your probability of making a mistake on future examples that are drawn from the same distribution. Obviously, you don't want to just try to get low error on your training data. You can do that always by fitting a polynomial. You can always get perfect error on your training data. The hard part is getting error on future examples drawn from the same distribution.
You have, you call it learner of big F and not little f. Does it mean you actually have a distribution of functions you want to?
No, okay, good point. So the model says that this algorithm learns the family of functions if for every function in the family, f, for every f in big F, and for every distribution over x, you get this kind of guarantee.
See, it's not like that you have, like when people have a distribution,
no.
You usually have a distribution of functions you want to learn. You assume there exists one deterministic function which you have to learn.
Right, exactly. So this is sort of sometimes they call it distribution free, because you're not assuming anything about the distribution over x, and it should work for all functions. It's not kind of a Bayesian approach. Okay. And of course, you would like you need this algorithm to be a polynomial time algorithm, so it should run in time polynomial in the number of samples it gets. And also, the definition requires that you get error less than epsilon with a number of samples that's polynomial in 1 over epsilon. Okay, so you can get your error arbitrarily low using a polynomial number of samples. And oftentimes, this is parameterized by some n. So like in the diabetes example, you have vectors in n dimensions, and you now want your algorithm to run in time both polynomial in n and 1 over epsilon, or the number of examples should be polynomial in n and 1 over epsilon. Okay?
Why do you call it agnostic?
So this is not agnostic. This is the original, this is called PAC, which stands for probably approximately correct. The approximately correct refers to the fact that you get error less than epsilon. You can't guarantee error 0. And the probably, actually something I didn't mention, refers to the fact that You can't get this always. You may always have there's always a chance you'll have a bad data set or a non-represent. You could get the same point every time, for example. So you can get these kind of guarantees with high probability, or equivalently for this talk, I'll just say you'll get them in expectation. So the output, the hypothesis you output depends on the samples that your algorithm gets, and its error is a random variable, and you want, say, its expected error to be less than epsilon. Okay. And okay.
So in your the diabetes example, then F and H are what?
Right. So F is the truth about what determines whether someone gets diabetes, and H is your prediction. Note that H is not necessarily a member of this family. It's just some other rule that you concocted that, you know, if their blood pressure minus their height is bigger than 7.
Still confused because you must have somehow two measures around, because the error of H is already the probability with respect to some measure mu, and then you take also expectation.
Okay. So the error of H is with respect to future examples drawn from the distribution. So for any H, I can define its error, meaning what's the chance it'll mess up on examples drawn from this fixed distribution mu. But what H do we learn? Well, that's going to depend on the training data, which we got over here. And that depends on which samples from mu we got, in addition to the fact that this algorithm may be a randomized algorithm. But let's forget about that for a second. This algorithm depends on which examples we got. So if we never saw, you know...
so should I think of the error of H, you do P mu conditioned on the sample, on the test sample you got, and then you take the expectation of...
yeah. Okay. Or you can just think about, given m training examples and one test example, what's the chance we get that one test example right? And that's equivalent. Right, good. And feel free to ask questions. I've got plenty of time, so I don't have to say that. But okay. So, all right. So this is the PAC model, which is a nice model. And how many here have seen this PAC model before? Just so I know. Okay, a lot of people. Okay, great. All right. Okay. So in our case, we're doing half spaces. So what is a half space? A half space is, you know, half the space, which is basically an indicator function in n dimensions of whether w dot x is bigger than theta for some vector w in n dimensions and some real number theta. Okay. So for half spaces, what happens here? You get your samples from the distribution. All right, and you know, they're labeled according to this true function f, and you have to find some other function h, which is going to be accurate on future examples from the distribution. And this is a relatively easy problem. Actually, all you have to do is, if you find some consistent half space, which is a problem in linear programming, and then you output that half space, and you can argue, it's not too hard to argue that if you take enough points, then the error of this half space, which is consistent with the data, is going to be low on future examples from the same distribution. If it had high error, if there was a large region here with a lot of probability, probably you would have seen some examples there already. So this is just how you could learn PAC-learn half spaces in a noiseless model. Okay.
So how is this related to? I'm just ignorant, so I will ask you all my dumb questions.
Great.
So how is it related to support vector machines?
Oh, so support vector machines are a way of. Are you asking how my talk is related, or how this example? The support vector machines kind of start with this picture usually, and they have oftentimes they even assume there's a margin between the positive and negative examples, meaning that there's a separation between positive and negative examples, and they give a different algorithm for doing that. But then they throw in this reproducing kernel Hilbert space stuff to mix things up, and but at their heart they're really solving the same problem, just possibly with in a higher dimensional space. Good question. So okay, so that's the PAC model, and just to orient yourself, there's some things you can learn in the PAC model and some things you can't. For example, or we don't know. So for example, these DNFs. It's one of the classic long-standing open problems. Can you learn a DNF where a DNF is some formula like that? And nobody knows whether you can efficiently PAC-learn DNF. But the reason I bring this up is it turns out if you could agnostically learn half spaces, then you could actually PAC-learn DNF. So, okay, and I'll define agnostically learning half spaces in a second. but just to orient yourself. Okay, so very natural if you want to talk about noise to consider IID noise, where you have a function f eta, which is just f corrupted with probability eta. With probability eta, you switch the label. With probability 1 minus eta, you don't. And now your goal, of course, you can't get error epsilon because your error is your chance of guessing f eta. So you can think of f eta as a randomized function, which is independent for each x. So with each x, independently, we decide to flip the bit with probability eta. So of course, you can't expect to get error less than eta. But you can hopefully get error eta plus epsilon. So in this model, that's your goal. And in terms of half spaces, what you have here is just a bunch of random points, each one flipped with probability eta. And of course, you want to output some example A, some hypothesis H, which is going to be accurate on future examples. Okay? And also, this is what you can learn in the noisy model. Another nice problem in the noisy setting is this classic problem called parity with noise. So this is a great problem, one of my favorite problems. And nobody knows whether you can efficiently learn it also. And basically, it's a mod 2 version of the half space problem. So you have a bunch of equalities. So you've got some hidden vector s now, which is 0, 1. And the function is 1 if s.x is 1 mod 2. So I guess f of x could just be written as s.x mod 2. Sorry. So somehow when you add noise to this problem, without noise you can learn that, but when you add noise to this problem, nobody has any idea if it's possible, and people have used that as a basis of crypto systems, and so on. And of course, you might expect, I was going to say, if you can agnostically learn half spaces, then we argue that you can learn parity with noise. Okay, so.
Which means you could write some crypto systems.
Yes, yeah. And also, it has a lot, this is a great problem also because it has other applications. So if you can, turns out if you can learn parity with noise, you can do things like decode random linear codes efficiently for some range of parameters, and that would be a great breakthrough too. So as you can see by all of this, probably we don't solve this problem completely, but we do make progress on it. So let me finally get to defining what the problem is that we're solving. Okay. So what does it mean to agnostically learn a family of functions? So here again we have this distribution, but now we have just this arbitrary function. Okay. You can think of it as arbitrary noise. Okay. So you have your data is labeled by an arbitrary, possibly randomized function f twiddle. So that can essentially model any distribution over xy pairs. So there's really no assumption on what's going on here. So you can think of it, now you can think of it as there being this true f, the truth function f, and you've got sort of adversarial noise. Okay, so you've got some distribution which is adversarial. Or you can just think of it as, there's this arbitrary distribution over xy pairs. Okay, and what is our goal now? Well, we don't even know, there's no eta, we don't know what the error rate of the best function is. But let's define opt. Okay, so opt is now the error rate of the best function in that class. So if we look at the functions in the family, what is their error rate on future examples? Opt is the error rate of the best function in the class. And our goal is to get error rate optimum plus epsilon. And I think the reason this is called agnostic learning is it's sort of a matter of belief of whether you think, is there really some true function and some adversary came and put noise, or is there just the distribution of data in the world as we know it, and our goal is to do as well as the best function in the class?
I'm sorry, the example's really helpful. So
okay. So right, in the diabetes example, say, you don't expect the data to be perfectly distributed according to some half space. Even though you want to learn half spaces, you don't expect the data to be perfectly distributed according to half space. You don't expect the data to be random, independently noisy with some fixed probability. You just have some distribution over data, and you would like to do, say, as well to learn half spaces would mean you're doing as well as the best half space, the best rule.
So does best mean maximum likelihood?
No, best means minimum error. So the error on future examples. Right. So this is different than a Bayesian setting where you might have a prior over, hypotheses, and then you might do some updating. And I mean, that's a great kind of learning too, but this is a different notion. When you can get it, it's kind of a very strong notion. It says, look, I'm doing as well as the best rule. What more can you ask?
You assume there exists a best route, so...
Well, there always exists a best...
Sure, but it's sort of, right, there may be situations where we actually know that reality is not one function, but
yeah, sorry. So in the Bayesian setting, you might have a prior, which is very accurate, and it can help you learn faster or more accurately. I mean, this will learn half spaces, so don't think eventually. If you could solve this problem, I would argue you could learn half spaces.
Platonic would be closer.
What'd you say?
The Platonic would be the...
What's the Platonic?
I mean, you assume that there is a nice truth out there.
Yeah.
You only see the distorted image of it.
Right.
So when they're coming from the same distribution, opt is 0, and then the system opt goes up as these distributions become more and more mismatched in some sense.
Right. So in the PAC model, we were assuming opt was essentially 0. And here you've got just some arbitrary distribution. Here, let me show you for half spaces. Here you've got some arbitrary distribution, who knows what. And the question is, there's some best half space, let's call that F, the one that makes the fewest errors, not on the data, but on the distribution. And, or you can call that the truth, if you like. And then the distribution is what it is.
Why would that not just be the least squares?
Okay, so this seems on the surface related to a linear regression problem. So linear regression, you would try to fit this by a linear function. And least squares is great because you can efficiently find the best linear function to approximate any data set, and it's great and very fast. But here, what's going on that makes this problem harder is that we're looking for discrete classifiers, 0, 1. So we want to make predictions which are 0, 1 as well. Maybe we want to make a decision, should we operate or not. And so having a real number may not, in fact, sometimes having real numbers is exactly what you want, and sometimes what you want is a discrete prediction when you're doing classification. And so this is the problem of finding the best classifier.
H does not have to be from the family FM?
Exactly. So H doesn't, so in fact, yeah, here, look. H, so, and in fact, it's NP hard to solve this problem if you require H to be from the family. To get a full, to meet this definition would be NP hard if you require yourself to get the best function.
You mean when epsilon is 0?
No. So even to get an algorithm that's fully polynomial in n in 1 over epsilon is NP hard. But in fact, it's even NP hard to get to within say opt plus some constant. I think it's like 0.004 or something. So even to find any half space that's accurate to within that, I think there's even a better number. But basically, it's NP hard to get any half space which is that accurate.
But once H is not from the family, then in principle its error can be smaller than that of O.
Yes, sometimes its error can be smaller.
The goal is...
Right, but still, I mean, if we want to talk about learning a family, we can't guarantee it's smaller. We want to talk about learnability of a family of functions, we just mean that you're doing almost as well as the best. And if you don't like, if you think you can do better, maybe you want to change your family of functions to make it richer or something so you could do better.
So now I'm confused. Wait, earlier you said if we could solve agnostic half-space learners, we could do all these things, and now you're saying it's NP hard, or is there?
Okay, so there's something called proper learning. In proper learning, you assume that you require that H be in this family of functions F. So proper learning is to this accuracy is NP hard, but we don't know whether it's possible or not. If you in our model, we're not requiring this proper learning. We don't know whether it's possible or not. If you could do it, you could solve all these great problems. There's no reason to say that it's necessarily hard. I mean, it may be hard, but...
Can I picture it as follows? If I have just some family of functions,
right.
What I could sort of really learn precisely would be eventually this family of functions and the probability distribution on it. I mean, I could hope with infinitely many runs I could sort of learn that.
Right.
And sort of what we do instead of learning this family of half spaces, we learn the best function which sort of approximates it without being a half space itself.
Right, yeah. So what's kind of going on is a relaxation. I mean, sort of, actually, a great algorithm for this is just find the best half space on the data. Okay? Given a data set, find the best half space. Okay? In 2 dimensions, you can do that. In d dimensions, you can do that in time. If you have m examples, m to the d, because you look over all, there's only m choose d different points, and each half space is determined by d points, so you can just find them. And that's a great algorithm. It gives you all these guarantees. It solves the problem in all three models. All three models are information theoretically equivalent. The whole issue is a computational one. Nobody knows how to efficiently find the best half space. In fact, that's an NP-hard problem. So, so we can't solve that problem. So essentially, it's a computational one. We're playing a computational game. We've sort of relaxed the model to allow us to output functions from a larger set, and then we're able to solve this problem in some sense.
So, actually, the fact that you're talking about half spaces here only comes in the value of opt.
Right. Right.
The algorithm itself doesn't matter. I mean, you just want to find a
yes, exactly. And in fact, the algorithm
good description of the data set.
Yeah, and the algorithm, the particular algorithm we have, is very much like these Fourier learning algorithms, which have been applied to many problems, and our algorithm can be applied to many problems. We just chose half spaces because it's one of the more fundamental examples, and we can say something about it. So that's what the focus of this talk is. But in principle, you can use these approaches to learn your favorite class of functions.
So except for the function op, the half spaces, they sort of, do they even enter into your data set?
Nope, nope. I mean, you have the same data, you have some distribution labeled by some function ftwiddle, whatever. You have this joint distribution.
And ftwiddle is not, but ftwiddle is in the set, right?
Nope, ftwiddle is not in the set. Ftwiddle is just an arbitrary, let me go back. Ftwiddle is just some arbitrary function, even randomized function from x to 0. So no assumption on the data. So it's a great model. I mean, I really like their model. Oh, this model was due to Kearns, Shapiri, and Selly. And I think it's the most natural model of learning, and it's very nice what you can do information theoretically in all of these models. There's a nice clean theory. It's something called the VC dimension. So if a class of functions has a finite VC dimension, then you can learn it. If it doesn't, you can't. All three models, it's the same, it's equivalent. So it's an elegant theory, but the whole issue is when you start putting in computational restrictions, when you require this algorithm to be polynomial time and to get error, yeah, they require the algorithm to be polynomial time, then that's when, you know, it becomes interesting.
Why the heck are you interested in this half space? I mean, the data don't come from a half space.
Right, but
algorithm
good. So you might say, let's just try to learn as well as the best function, but that's impossible. You can't. You need to make some restriction on the class of functions that you want to compare yourself to. If you just say, oh, my goal is to learn as well as the best function.
I mean, it's sort of like saying, well, it's like saying, to be politically incorrect, I know there is no God, but let's sort of try to find the data, the function which approximates best the assumption that it's either Christian or Muslim or whatever.
But you know, I mean, that here there's no God assumption, because you know, and empirically that these half spaces, many times there are half spaces that do pretty well. And you know, people are calling for
empirical fact.
Yeah,
that's not.
Yes, right.
No, I mean, that's an interesting theoretical question. Why
right.
do half spaces?
Right. Also, these half spaces are kind of these generic things. So there's many other representations you might want to learn in computer science. Like there's these decision lists. You know, a decision list is you check, you know, various things like if they're, you know, if they have a family history of diabetes, then you'll predict 1. If not, you go to the next node and you check some other attribute x3. If the third attribute is 0, then you predict 0. You can define all kinds of interesting concepts like this, and this is an old one. And this can also be represented as a half space, turns out. And also, you know, very natural classes like a disjunction, you know, x1 or x3. This is a half space. Now the big set x, xn is just 0, 1 to the n. Okay, and this here is the half space, you know, x1 plus x3 greater than or equal to 1. This disjunction. So half spaces are nice because they represent a large, many other families of functions as well. And in fact, this very simple, this is like one of the first examples you always give when you talk about learning an OR, right? And in fact, nobody knows how to agnostically learn ORs, even. So, So that's kind of the state of agnostic learning, and it's NP hard to agnostic learn ORs if you require yourself to learn an OR as well. So the state of agnostic learning is kind of sad, actually. There's all these negative results. Information theoretically is possible, but computationally, all these negative results. Okay. And just as I mentioned, the whole issue is you would really like to just find the best half space, which can be done in time exponential in a dimension. That's called this curse of dimensionality. I love that expression. The curse of dimensionality is that these problems can be typically solved, but in time exponential in the dimension n. In this talk, we have our main result is basically a polynomial time algorithm in the dimension under two assumptions. Okay, so first is some assumption on the distribution mu, which is, I'll argue, reasonable or whatever, but if we call it the reasonable assumption, then it is reasonable by definition. And so what is that? It's something either the functions can be uniform on a ball or in a sphere, in the hypercube, log concave functions. So there's a number of distributions. There's a number of distributions that we can handle there that I'll talk about later. And the bigger restriction is that it's polynomial in n, but it's not polynomial in our accuracy epsilon. But the reason is that kind of interesting is that we're somehow getting a dimension-efficient algorithm. So still, if you say, OK, the optimal half space has error 10%, and we set epsilon to 0.01, so we get 11% error, fine. But that won't, the algorithm is still polynomial as the number of dimensions increases. Okay, so fix epsilon to be your favorite constant, and then this algorithm is polynomial. And that's what's kind of interesting is that, oh, we're avoiding this curse of dimensionality. Okay, so let me go ahead and give the main theorem. So our algorithm, which is just a modification of this Fourier algorithm, gives you this error, the kind of error you want, almost as well as the best half space. It's polynomial in n. We're going to fix the epsilon constant. And what kind of distributions does it work for? Okay, so log concave distributions, which are distributions whose density is the log of the density is a concave function. And so its support is a convex set. So actually, uniform distribution over any convex set is log concave. And we're talking about the distribution over unlabeled examples here. It says nothing about the function that's labeling it. An exponential distribution, a multinormal distribution, it doesn't have to be symmetric, Gaussian, it doesn't have to be symmetric. So all these things, most continuous distributions you think of, or many of them, are really log concave. No. Okay. Yeah, so that's true. That's the Gaussian. And none of the power law distributions. Okay, so when I talk about reasonable and I say this, it's not
Cauchy, most people would consider Cauchy to be unreasonable.
Okay. So what is not log concave? Cauchy. Uniform distribution over a hypercube or a sphere. Anytime the surface of a sphere, anytime your set is not, the support is not convex, it's not not log concave. But so in this case, for example, uniform distribution over the hypercube or sphere, the algorithm also works. Okay, so it's kind of interesting to think about when the algorithm may not work. But so this is the guarantee we get. And actually, we can provide explicit runtime bounds for the case of the sphere and the hypercube. And it is the n to the 1 over epsilon to the 4th. So the epsilon is in the exponent for those two cases. But here we just know that there's some function that's determining this, but it may be doubly exponential in epsilon. OK, so are there any questions about the main theorem?
What about the low weight Hamming kind of points in the sphere which have low Hamming weight? Not uniform over the whole sphere, but
You're talking about on the sphere, not on the ball.
on a Hamming cube.
Oh, on the cube. So fix some weight.
For example, those of very low weight.
So 0, 1 to the n,
And take only vectors that have 3 ones in them.
I think it should work, but we didn't analyze that case. But this, yeah, that's my intuition, because to me, the hypercube. So the hypercube analysis, actually kind of interesting, was done before. I mean, this is the Fourier style analysis. The sphere is something new that we did. And the nice thing about the sphere is you can kind of use geometry to analyze this. Whereas here you use noise sensitivity or something else. But to me, they act very similarly. They actually have the same exact degree bound. And what you're asking for, I think, is a kind of a cross-section, a hyperplane intersecting with that. And so here, if you took, say, the ball, which is also like the sphere in our terms of our analysis, and you were to take a hyperplane, intersect with that, or some convex subset of that, you would have the guarantees. So my intuition is that it would work for that, but I haven't analyzed that.
He's talking about a ball, not a hyperplane.
What'd you say?
He's talking about a ball.
Okay, fine. That's still a convex set. Right. No, I mean, he's talking about an L1 ball set, so, okay, whatever. Yeah. Okay.
Why do you carry on the opt? Because once you fix half spaces, opt to 0, and this is equivalent to just restricting yourself to half spaces, right?
So
with opt 0.
No, sorry, we haven't. No, if opt is 0, then all of this is solved because this is the pack learning. So if you knew opt was 0, then you just have to find some consistent half space with the data, and that you can do with linear programming.
But what about mapping it to the opt and the difference between the opt and your estimate, two-way error estimate? I mean, the errors only will, since it's Boolean, if an error on an error would just help you, right? So you're getting a worse bound if you just try to approximate the opt.
You're saying you can do better than opt?
No. I mean, so you fix the opt of your function.
Yeah.
I mean that f in the half space, and you try to approximate that function. You can do that with an epsilon, and then you get this kind of.
That's actually hard, right?
Yes. So if you could do that, then you would get this guarantee right away. But that algorithm, unfortunately, is exponential, or at least we don't know how to solve it faster than exponential in a dimension.
I'm sorry, I was watching the talk of a video. It took me 1 minute to come here, so I may have missed 1 minute. The thing that worries me about what you said, unless you said something to mitigate that, is that in many problems I have multiple classes. Each class has a distribution, and now I have to do classification over the whole space, which means I have a sum of log concave distribution. Or do you have any result of that? Or
Usually you're talking about multi-class classification.
Yeah.
So.
Well, even if it was not a multi-class classification, if it was just two classes, I would have, a bump here and a bump here and multiple bumps, and then what do you do?
Right.
Is it out of your...
Yeah, so I don't even, I mean, I can concoct examples which are, the average of two Gaussians, which I don't believe you can use this. I think you can show that this won't work. But especially as it would actually depend on the separation of the Gaussians. So you could maybe put a bound in actually that depends on the separation of the Gaussians. But in the general case, if you want to get two Gaussians of arbitrary variances, then actually that could be hard for this approach. Okay, so previous.
Do you say that in that case agnostic learning may be NP-hot?
So we don't know whether agnostic learning, just as Amat defined it, we have no idea whether it's possible or not. So good question. So just mentioned some previous results. So this perceptron algorithm can get some kind of guarantee where in n dimensions, if you're on, say, this uniform distribution on the sphere, it gets something that increases with the dimension, and it's polynomial time. It's a very fast algorithm. This is typical for agnostic learning. Oftentimes you can get these kind of guarantees. And as I said, it's NP hard to find the optimum plus 0.0 for half space if you are required to output a half space. Okay, so I've defined the agnostic learning problem. I've hopefully convinced you it's an interesting problem related to many other learning problems, and I've said what kind of progress we make on it. And next I want to talk about our algorithm, which is just fitting polynomials, and how it relates to this Fourier algorithm and actually to the support vector machine algorithm that you mentioned. And then I'll talk a little bit about the analysis of it. Okay, so now to the algorithm. So, okay. So you've got the input to the algorithm is some m data points, okay, which we can graph here in one dimension. It's very simple. You have x is just the real line, and you get point 0 or 1, okay? And of course, the half space in one dimension is very easy. It's just a function like this, step function. And in one dimension, the problem is easy, of course. But how does our algorithm work? So basically, we're going to minimize the error of a degree d polynomial. So we're going to take our data, and we have some parameter d, which we set according to the amount of data and the number of dimensions. And then we find the polynomial of degree at most d to minimize the absolute error. So this is not the squared error, which you guys are used to minimizing the squared error polynomial, but this is the absolute value error. But still, it's a convex problem if you think about the coefficients of the polynomial. So if you write this down as in terms of the coefficients of the polynomial, you can solve it and find some polynomial in d dimensions which minimizes the average absolute value error on your data set. So actually, you can write it as a linear program, and it's still size polynomial in the number of dimensions for the parameter we've chosen. So and actually, you don't even need to use linear programming. It's a special kind of problem, and you can use faster methods. Okay. But basically, it's a polynomial time algorithm. And then next, we need to, the problem is that this polynomial is just outputting real values. We actually want to output predictions in this case, a 0, 1 prediction. So the natural thing to do is threshold the polynomial somewhere. And we get to choose where to threshold it. And notice that we're going to make a mistake if our threshold lies in between the polynomial and the data point. So we're actually going to choose the threshold that minimizes the number of mistakes on the data. So if you sort the data according to the y values, it's pretty easy in one pass to find the threshold that will minimize the number of mistakes on the data. Okay, there's only m data points. So we find the threshold that minimizes the number of mistakes. We use that threshold, and we're going to output now the function that predicts on future examples. It will predict 1 if the polynomial is larger than theta, and 0 if the polynomial is less than theta. Okay, so that's the algorithm. Just fitting a polynomial to the data. Any questions?
Are you going to explain how to generalize to more than one dimension?
So I drew it in one dimension, but what happens in n dimensions is this polynomial is the sum of terms, and each term has a coefficient, and you need to find the coefficients of the polynomial. Even if it's multidimensional, it still has a bunch of coefficients. So in many dimensions, if there's a degree d polynomial in n dimensions, has like n to the d different coefficients. And so you just need to find each of those coefficients.
Well, why aren't there an exponential?
So n to the d is exponential, but we're going to choose d to be pretty small. In fact, for many of our applications, it would be suffice to pick a constant degree, so that the algorithm would. That's why the algorithm polynomial time.
Also, just empirically, I don't know, maybe people would use mean squared error, but even polynomial fits tend to empirically work really, really badly. That's like usually a really incredibly bad idea on empirical data.
Okay, so I'm going to talk about next how this relates to support vector machines with a polynomial kernel.
Yeah.
It's a reasonable algorithm, and I think you may be able to analyze. These support vector machines are doing something, as I'm going to talk about in a second, they're doing something very similar. So I agree that maybe, well, one thing is that I do think that this least minimizing the absolute value as opposed to the square can help a lot. And I think that's one of the things you get from these support vector machines. But here we can prove something about them, how well they do. Okay, any more questions?
In the first step, you find this polynomial, and in the second step, you readjust the constant term, so to say.
Right. Kind of a...
I was just wondering if...
You could do them together?
Yeah.
Good. So that's a good thing to mention. So suppose you could do them together and find the best polynomial and threshold. In fact, the problem we're trying to solve is a threshold of a polynomial of sorts. It's a threshold of a one-dimensional polynomial. So...
Is there a dark...
Oh, okay. Yeah, here. Yeah.
Throw this one out.
Okay. So we're looking at this. This is the problem we're comparing ourselves to that. If we could just find the best thing of this form, which is a one-dimensional polynomial thresholded, we would solve the problem, as I said. But we can't. So what we do is we fit the best degree d polynomial, and then we find the threshold afterwards. It's kind of just a relaxation of the problem. Okay? But good question, because it's confusing. We're trying to learn a threshold of a one-dimensional polynomial. Why are we using these high-dimensional polynomials? Why don't we just use a one-dimensional polynomial? Well, we could do linear regression which is almost essentially what the algorithm would do in one dimension when the degree is 1. But then we're going to threshold it afterwards. Okay. And I don't think I really have time to talk about the analysis. Oh yeah, I don't have time to talk about the analysis. But I have a lot more slides. I'd be happy. It takes, to analyze this algorithm and show that it does almost as well as the best low-degree polynomial. So if the class of functions can be approximated by low-degree polynomials, then this algorithm will do agnostic learning. Yeah.
Are you also saying that the smallest d is 1/4 log m? How is that?
Oh, so where is this parameter coming from? Well, this is just one choice of the parameter. I mean, you got to be careful not to choose a degree that's too large. I mean, you don't want to choose a degree that's so large that you can just fit all your training data with a polynomial. And this choice is, well, if you look at the number of parameters in a polynomial of that degree, it's n to that power, so it's like m to the 1/4. There's only m to the 1/4 parameters, so you can't overfit m points that well. So that's how we chose that parameter. But you could choose it. You could also choose it. In practice, you probably choose it, depending on what gave you best performance.
Can you say a word on how log concavity comes in?
Yeah. I'm going to get to that. Good. So, okay. So let me just mention the similarity I'll just skip over. Just mention this Fourier algorithm, which many of you are familiar with. Okay, the way I think about it or relates to this problem is it only works for the uniform distribution on the hypercube. Okay. Don't mess with the symbols if you don't know. And basically, when as the number of points goes to infinity, or basically it's an approximation to the least squared error, which you can solve actually for any distribution. You can find the polynomial that minimizes the squared error. But they use a trick that works only when the distribution is uniform. And then they threshold at the point half, essentially. Okay, so that's how it differs from our algorithm. Point 1 is that it only works for the uniform distribution over the hypercube, even though you can run this approach as well over an arbitrary distribution. So I would think you might as well do that. And also, if you analyze it in our agnostic setting, it'll give you some kind of error like this. So you get a bound, not optimum plus epsilon, but 8 times optimum plus epsilon. So that's kind of, our starting point was actually this algorithm. Our algorithm is a generalization of this. And we said, okay, you get error 8 times optimum. And so, can we fix it? And that's how we fixed it. And then we realized it could be extended to log concave distributions and so on. Okay. And also just to relate to practice, so there are these support vector machines which are very popular. And actually, our algorithm is very similar to what they're doing when you consider one of their cases. They have this kernel in a reproducing kernel Hilbert space, and if you choose the degree D polynomial kernel and you have no regularization, then essentially their algorithm can be thought of in the same way. And basically, it's the same as our algorithm. It's minimizing the absolute value. The only difference is it doesn't penalize the polynomial when it's too right. So if the polynomial is on the right side, but it's off by it's right by a certain amount, then it won't actually penalize the polynomial. Okay, so it's not an absolute value error. It's absolute value error, except we don't charge when you're too right. When you're too wrong, we still charge you for the distance between your prediction and the point. When you're too right, that happens. And they also threshold at one fixed point. It turns out that actually, if you use their algorithm and you threshold at the best threshold, which I don't know why they wouldn't do.
We do.
You do? Okay. Then you get the same bound. So one way to look at this is to say that this is an analysis of support vector machines showing that they agnostically learn a class of functions of interest. So there's been a lot of work in the support vector machine community, and then there's this like pack learning, and they're very disjoint. So I don't think support vector machines have been shown to pack learn much. They can learn half space, but I mean they can learn. They haven't been shown to be very powerful in that sense. So there's sort of a disjoint between that. And here's one way to say, oh, look, they do something pretty cool. They agnostically learn half spaces, which is something that no one, or to an extent, which is something that we didn't know how to do before. Okay, so we talked about the algorithm. Now let me just discuss the analysis a little bit. So I should probably finish in like 10 minutes or so? Or?
Well, you started 10 minutes late,
okay.
So you can certainly
Okay. So, and yeah, if you have specific questions, this is great. I much prefer to answer questions. So if people have technical questions or specific questions, ask them. Yeah.
So what is the relation with Fourier analysis?
Okay, good. So the Fourier algorithm is just, which I didn't get into, but there's this basis of, Fourier basis of terms like that, and which are just okay, if you
explain it a little more.
Good.
I know it, but
okay, so if you're just over the hypercube, then what happens in the hypercube? If you want to write a polynomial in the hypercube, you never need an exponent larger than 1, right? Because if you're in, say, let's say you're in minus 1, 1 to the n, and you want to write a polynomial here, so you don't need any terms with exponents, larger than 1. You never need x3 squared because that's going to be 1 only. So you have a sum of terms with coefficients, okay? So you can write each term just as, each term can be written as a product over some set S. So xi, so this you would call chi sub s of x. And a polynomial in general can be written as a sum of coefficients, c sub s times these terms. Okay? That's just a way of writing a polynomial here. And then there's two ways to estimate such a polynomial. One of them is say, okay, I've got these coefficients. And typically you look at it a degree d polynomial, so you look at the size of the set at most d. So there's two ways to solve this. One is to say, okay, I've got these coefficients, and now let me look at my data and find the coefficients which give me the best squared error on the data. And that would be just regression, solving this problem. And you can solve that for an arbitrary distribution. But in the special case where the distribution mu is uniform, if you take the uniform distribution on this set, so you take uniform distribution over that set, then you can estimate these coefficients in a very simple way. Just look at, on your data, you evaluate each of these terms up here. And you take the average product of the term with the label yi. Sorry, that's true when the labels are minus 1, 1 instead of 0, 1, but it's not a big difference. So that's how you can estimate these coefficients. And so that gives what this celebrated algorithm of Linial, Mensur, and Nissan, which I forget the name. It's a great algorithm, and it's had lots of applications. So since they introduced it some time ago. So it can be shown to learn all kinds of interesting classes of functions, as long as you can show that the classes of functions can be approximated well by polynomials. In fact, look at the special case. Typically it's looked at when opt is 0. If opt is 0, then this is pretty good. You're getting a guarantee of at most 8 epsilon. You wouldn't need to do all the improvements that we suggested just to get error epsilon instead of 8 epsilon, at least theoretically. But we're considering the more general case. So does that answer? And also, so this. Okay.
Keep going.
So this, and you can use our algorithm there, the L1 regression algorithm, on many problems, and it works as well as the best of many classes of functions, not just half spaces. But in this talk, we just analyze half spaces.
So going back to the SVM link,
yeah.
The question, it was confusing that you don't access all of the possible polynomials up to n to the d when you pick one specific kernel. So I'm sort of confused about the link between your general polynomial fit and the thing.
So,
can you explain that? Is there a step missing, or is it
so the so there's this representer theorem that says that basically any polynomial, the best polynomial at least of degree d, will be able to be represented by a bunch of support vectors. So this kernel you define k of xy is, or I should xz, or xt as I say, is 1 plus xt to the d. And this can be, you can write it that way, but you can actually think of this as just a standard dot product between two vectors in some larger space.
Why does this help? I don't quite see.
And this larger space has a term for each of the terms in the polynomial of every degree. So kind of got two different groups of people here, but
that's right. Now I remember, because that's true for this particular kernel. So is that, will that map? Can you choose the kernel order to map to make sure that you don't get any more than 1/4 log n?
Yes. So you choose the degree of the polynomial kernel to be exactly that when you run the algorithm. Yeah.
Okay.
Okay. So these are great questions. Okay. So let's talk a little bit more about the analysis. So we have this lemma saying that our algorithm agnostically learns a family of functions. And for any family of functions, it will work, but it has some dependence. So it has an error rate, which is the optimum of the minimum of the function in the family, plus some term that decreases with m, the number of examples, plus some, and that depends on, that's basically how much overfitting you can do. If you choose polynomials of large degree, you can potentially overfit too much. So that's what comes from the VC dimension argument. And then there's another term here which depends on how well you can approximate the family of functions by degree d polynomials, which in turn depends on whatever distribution mu you're using. So if you can, if you look at how well do degree d polynomials approximate the half spaces in our case, that depends on the particular function mu. So we would define this quantity to say, it's a lot of notation, but basically, how well can we approximate every half space? So every half space should have an approximation by a degree d polynomial, which gets error, squared error, less than this quantity. All right. So why do we use squared error? It's just mathematically easier to analyze. But the absolute value error is bounded by the square root of this quantity, which is why the square root is there.
What is the lemma? The lemma is the statement in blue?
The lemma is what? A statement in proof, right. But I don't prove.
Blue.
Oh, in blue, yes. The lemma statement says, yeah, for any family of functions, the expected error of the algorithm is at most this quantity. Or this term here is defined here, and this holds for any family of functions. So in order to analyze it in general, we have to do two parts. For half spaces, we show that it works for any family with this quantity, and then we have to bound this quantity for different distributions and half spaces, since that's what we're interested in.
I'm a bit confused. So you say this delta term, it's how the degree d polynomial approximates error for f, but if f is a half space, then the degree d polynomial is a special case of a degree d polynomial. Zero.
No, half space is not. No, half space is a threshold of a degree d polynomial. A half space is not a degree d polynomial by itself. Right, that's a common question. So a half space is a threshold of a degree polynomial. So the question is how well, I mean, in one dimension, this picture is misleading, but in one dimension, you've got the half space, which is, this, and you're trying to approximate it by a polynomial, which is that, something like that, right? And this is not a hard lemma to prove at all. So I could give the proof, but I don't think that would finish all my time.
Can you still give some idea? Because naively, I would think in order to prove that you need a lower bound on opt, and that seems sort of hard.
Okay, good. So the point is that you've got your data. There's some polynomial though, which there's a best function in the family, which I called f. Okay, so you've got your data, which is somewhere, and there's some best function in the family. If it's half spaces, there's a best half space. Okay, but we've assumed here, for this delta term tells us that there is an approximation to f by some polynomial, which we don't know. We don't know f, and we don't know this approximation. Let's call it q, which is a degree d polynomial. Okay, we don't know either of those, but still these exist. Our algorithm finds the best degree d fit to this data. So it finds some other polynomial, which could be better. I don't know. It could actually fit the data a little better. P. And what we know about P is that it has error, at least in the absolute value sense, better than Q on the data, because we found the best fit on the data. So we know that on the data, the error of p, so the sum of p of xi minus yi, this averaged over the data, which I can write expectation over random data point I less than m. It's just a weird way to write that. Is less than the error of this other polynomial q. Right? So, and so basically what's happening here is, what is this term here?
I see, now you just estimate in the abstract how the best polynomial fits the half space.
Exactly. We're doing only better.
You're doing better, so therefore. Okay.
Exactly. Gotcha. And then you just have to, you just use the
polynomial in the half space would be nice. So now that will take exponential time to find, but you don't care because now you just use it for the error analysis.
Exactly. Yes, exactly. Right. So I think you got it. Right. The best function has some error epsilon. It's approximated, it's approximated to within epsilon by another polynomial, so by the triangle inequality. This is most opt plus epsilon. And then you have to convert from this to an actual error on 0, 1 when we threshold it.
So I see where your square error comes from. Where does the error m to the minus 1/4 comes from?
Okay, well, all of this argument will go to say that you're going to have good low error with respect to the data you've seen. That you'll fit the data you have well. But nobody promised that a good fit to the data is going to be a good fit to future data drawn from the same distribution. But there's the nice VC dimension argument, where the VC dimension says it basically a count on the number of parameters in your model. If you have a model with few parameters, and you fit data well with few parameters, like many fewer parameters than the amount of data you have, then you have a promise that you'll do well in expectation on future examples. And that's where this term comes. Okay?
And that's easy because it's linear. It's the threshold of something that's linear.
Exactly, the threshold. So the number of parameters is just the number of coefficients.
You know what VC is.
Yes, exactly. Yeah, we didn't have to analyze that. Right, exactly. Right. Okay, so that's the general lemma, and then you can use this in principle on any family of functions. So let me just give you an example of another family of functions. So disjunctions, which is what I mentioned over there, just an OR of variables. It's gone. So it's been shown by many people. This is Ryan O'Donnell, but when I when I made this talk, you didn't have. You see the resemblance? No. When I made this talk, there was no picture of Ryan on his webpage. Everyone else, I went to their webpage and took a picture. But so anyway, I think they were the ones to show most recently that.
You should put a picture on your webpage.
You can see me here too. So how can you translate what the symbol is?
This is a rhino. Ryan O'Donnell is like Ryan's mascot or something. That's it. That used to be his login at MIT, so that's what I chose. So basically, for disjunctions, okay, you get this nice bound actually that's independent of distribution. For every distribution, every disjunction can be approximated by a degree d polynomial to error, something that's decreasing exponentially with the dimension. Unfortunately, there's a square root, exponentially with the degree. Unfortunately, there's the square root of n term here. So basically, to make this statement mean anything, you need to use degree of polynomial at least square root n. Once you've got degree square root n, now you're golden and things are decreasing exponentially and everything's great. So basically, you can learn disjunctions using degree square root of n, which translates into an algorithm that learns using the previous lemma immediately to error up plus epsilon in time exponential and square root of n, okay, which is the best algorithm. So Avram Blum said this is one of his favorite problems because just such a natural problem. How well can you do compared to the best disjunction? And this is the best you can do so far. And it's for arbitrary distributions, okay? So now just to talk about what we would have to do to prove this, we would have to show that we can approximate polynomials for log concave distributions, for uniform distribution on the sphere, for uniform distribution on the hypercube. And here again we have Ryan to the rescue. So they've already analyzed the hypercube and shown, because there's been a lot of work, especially on the uniform distribution on the hypercube, to understand how well you can approximate functions by polynomials, and they've shown that you can approximate any half space on the hypercube using a degree, with degree d, you get error about 1 over square root d. Okay. And what's kind of neat is that you get the same kind of analysis on the sphere, same kind of guarantee on the sphere, but it's a very different technique. So they use noise sensitivity. And on the sphere, it's much more, well, it's just a different analysis is more geometric, and it uses a different basis rather than the Fourier basis. We use the Hermite basis. And also for the log concave functions, I'll say a word about that. But I don't really have time to go into detail on either of these, but I'm very happy to talk about it afterwards. The interesting thing to notice here is that it's all independent of dimension. So all log concave distributions can be approximated, any half space over any log concave distribution can be approximated to accuracy epsilon by the same degree. The degree of the polynomial you need is independent of the dimension to approximate any log concave distribution over any degree. Okay. And now I'll give away the intuition for that, which is basically, okay, you've got this great one-dimensional approximation to a half space in one dimension. What's going on is in n dimensions, of course, you can use the same polynomial in some other applied in some other direction, whatever the target direction is w, and you'll get a same degree approximation to polynomials in high dimensions. So that seems simple, and that's part of the intuition of what's going on. But in particular, you need to use certain properties. So you need to say, if you have a log concave distribution and you project down to one dimension, take the marginal, it's still log concave. So so now we got this one-dimensional log concave distribution. Also for a multinormal distribution, if you project down to one dimension, you get a normal distribution. And for the uniform distribution on the sphere, when you take the marginal in one dimension, you get something which is almost normal distribution. So actually it really doesn't depend on the dimension of the sphere. You always get something which is quite normal. So this enables us to kind of just focus on two different distributions. Our analysis boils down to a one-dimensional analysis on two different distributions. So one-dimensional problems are much easier, and it's much easier to solve them. And, so what are the two distributions? Can anyone guess what this distribution is here? What is this?
Bible?
No, it's a nu. Okay. All right. So, okay. What is the distribution nu?
We're not too fond of nu here, by the way.
What'd you say? You're not fond of nu. Okay. So basically, the two distributions we have to analyze are the normal distribution, just a standard normal distribution. It suffices to analyze one of them because all normal distributions are the same up to scaling and translation, and the scaling and translation does not change the degree of approximation. And can you guess what? Poisson. Oh no, that would have been good actually. Does that help? Rho, got it.
Yes, I mean, that should have been a
Poisson, you're right. Okay, you're right. Okay, so what is rho? So this is for the log concave distribution. So we use the properties of log concave functions, which are nicely laid out in a paper by Lovash and Vempala. Basically, all log concave functions have these exponential tails. And it turns out it's enough if you can upper bound one distribution by another. So if one distribution is about 10 times another, then this guarantee holds. And after you normalize all log concave distributions, they can be upper bounded by some constant factor times, say, this distribution. So that's kind of the nice property. And then we say, oh, we only have to analyze it for this one distribution. So now you've got a one-dimensional problem. You've got one distribution. You're looking at, basically, you're trying to bound, in one dimension, say, the expected error of your polynomial approximation, p of x minus some simple threshold function in one dimension for this one distribution rho, where x is in one-dimensional, chosen like this. So, you can basically all our theorem says is that you can approximate a polynomial arbitrarily well. We don't actually bound the degree you need. So it just says that eventually, as you take higher and higher degree polynomials, you can approximate any threshold function where the error metric is with respect to this function rho. Although actually different distributions, like if you took a distribution more like d rho of x, which is 1 over x squared or something, or proportional to 1 over x squared, I don't think you can approximate that at all. You'll never be able to approximate a polynomial on some some interval, let's say x minus 1 squared. oh no, sorry, x squared plus 1. You'll never be able to approximate polynomial under this distribution. It's not clear which distributions you'll be able to approximate all functions with, but you can do it for the log concave ones, just from this distribution. And actually, I mean, the way we actually came up with the numbers, it was easier just to plug into Mathematica this problem of finding the best polynomial. You can plot exactly how well are you doing. You can look at the curve, and you see that for this distribution, it's 1 over square root of the degree. And for this distribution, it's really logarithmic, so it's or you need an exponential degree to get convergence. Here.
What do you mean by you can see? Is that a proof? Or?
No, that's not a proof. So then you have to prove that you get what you get. So we didn't actually prove for this one that it's that bad, because I didn't feel like it would make our paper that much stronger. But for this one, we did show that, okay, if you have the normal distribution, which will apply to sphere, let's say, or to a multinormal distribution, that you get a convergence at a rate of 1 over square root of d. And so let me just say one word about how you do that. So there's this nice theory of orthogonal polynomials, and in particular, for this particular density function, you've got the Hermite polynomials form a basis of polynomials for a certain inner product, which is just the expectation of the product of these two functions under this weighting function. And so there, there's some sequence of polynomials and they're orthogonal, which means that the inner product is 0 for different polynomials, and they have increasing degrees. So these polynomials are very nice, and they let you just compute exactly the best approximation in the squared error to any function with a degree d polynomial, which is written in here. It's just like a Euclidean inner product. Here, these are the normalized versions of the polynomials. And then in order to bound your error, you just need to bound the coefficients of the inner products for a larger coefficient. So here you do that, and you can calculate it. There's nice recurrences for these things. You use those. It's just a little bit of algebra to bound these things. And you work it out. And actually, so for the case where the threshold is at 0, it's very straightforward to bound things. For the case where the threshold is arbitrary, we have to use some previous bounds that were conveniently already there on the magnet.
1990 or?
I think it's 1990.
Was it only done in 1990, that kind of stuff?
Well, actually, I don't know if anyone, I mean, we looked through books and then consulted people. I don't know if anyone actually worked out this example, which is a very simple example, like how well can you approximate a step function by the normal distribution. So we talked to...
Not in numerical analysis. I don't know, maybe I'm wrong.
Yeah, so we consulted with like Devore, who wrote... Yeah, right. So he said, anyway, everyone we consulted with said, you're doing exactly the right thing. The calculation you're doing is right. The straightforward calculation, it's fine. Maybe it's been in books or not. Anyway, so it works out. But sometimes they look at asymptotics in different terms. So what happens is they may look at the asymptotics as the degree gets larger and larger and larger, really large. We care about only kind of a certain range of degrees.
Probably faster for you to do it than find.
Exactly. Okay.
I agree with you. I mean, I had similar experience in some stuff in Lie groups where you sort all the group series would know it, and then they say, well, but we always ask different questions.
Right.
So I can quite well imagine that they've done similar things, but if you ask them for
coefficients of the indicator of a half space, this is just understanding the Hilbert transform.
I think it's probably,
and that's.
but it doesn't matter.
Really
He's not saying that's the main purpose.
Anyway, okay, fine.
Could be
fine. So for this is for the computer scientists. For the computer scientists in the audience, this is how the mathematicians do their analysis. Okay, so I think I'm just going to stop now because I've talked enough. But let me just say in conclusion that we had fun with these, studying this extension of the Fourier algorithm, and hopefully it'll have nice applications. Let me also say that this is not at all the only thing that I do. So I work on learning theory and noisy analysis and learning theory a lot, but I also do randomized algorithms and online algorithms, and I'm now getting a lot into game theory. So if you want to talk to me about other things, please feel free. And that's it.
One question.
So if you're building your whole theory on the sort of the BC bounds, those tend to be incredibly loose bounds, right? You actually plug in numbers that you care about, you get like bounds at 3,000% error.
Right.
I can bound anything at 3,000% error.
Right.
So when you say there's this constant epsilon, there's a bunch of hidden constants sort of inside.
Oh, yes.
You see what I mean?
Right, but I mean the flip side, I would argue, is that the algorithm we're using is related to these support vector machines.
You're sort of cranking the thing to the place where maybe they wouldn't necessarily. Have you tried your algorithm on real data sets?
No. So, but people have used these support vector machines with polynomial kernels, right?
With regularization.
You don't even need to regularize when you have the polynomial kernel because there aren't so many parameters. I don't know. I mean, we'll talk about it offline, but
There are possible there are support vectors, which might be as many as there are training instances.
Which could be very large.
Okay. I mean, so maybe you can listen. So this is an asymptotic result, and I'm not going to deny it. So this is only a result about asymptotics in the dimension. So it's not a proof by any means that if you run a support vector machine on a small data set, that you'll do well. But it is kind of, I'm trying to connect the two communities, because there's this community of people using support vector machines, then there's the theory community, which I don't think has seen any papers on support vector machines hardly ever. So it's kind of sad that these two communities are separate. So here's kind of something connecting the two, and I completely agree that it may not be interesting to practitioners because it's an asymptotic result, but it's still relating the two.
Did you put it in the regularization term? That's for everything up.
Well, to make it small enough. No.
That's exactly our point.
Maybe it would be interesting to try to go into this result and really get at what's going on. Maybe regularization can help you and improve the bounds. Maybe you can do better, and that would be great.
That's how Vapnik's theory for SVM started. He started proving a bunch of stuff when it was totally hard margin, and then other people sort of came by and added more theory for regularization. So.
Is it actually the case that your algorithm solves the agnostic learning problem where your class of functions is low-degree polynomials? And then you also prove a result saying that low-degree polynomials can very well approximate half spaces.
If your class of functions that you're comparing to are thresholded low-degree polynomials?
No, non-thresholded.
Okay, so you assume that there's some, yeah, of course, then it's easy.
To solve the problem?
No, I mean to show that our algorithm works. I mean, if there's some low-degree polynomial, it's very well approximated by a low-degree polynomial, so that delta is 0. So as long as your degree is as large as the degree of the low-degree polynomial, you'll do is what it's easy to show that low degrees of polynomials approximate low-degree polynomials, and then the lemma just implies immediately that you'll do agnostically. So the point is that with agnostic noise, so arbitrary noise, you'll do as well. But yeah, that would follow. But if kind of another question, if you talk about thresholded low-degree polynomials, those also would work because a thresholded low-degree polynomial is a linear function in an expanded set, so you could do that too. Okay. Thanks very much.
Adam's going to be around for 2 days meeting with theory people, and we